It's a pleasure to present our work on multimodal trajectory prediction of NBA players. This work was done by Nemanja Čurić, Vladan Radosavljević, Slobodan Vučetić, and me, Sandro Hauri. Recent improvements in computer vision allow for precise localization of NBA players and presents the opportunity to study the problem of human trajectory prediction with a rich dataset. Basketball players face difficult decisions at every time step, where they have to take tactical decisions depending on the positions of their teammates and opponents. Compared to the commonly studied problem of pedestrian prediction, the players show a much wider range of human locomotion, including quick accelerations. The publicly available dataset used in this study contains more than 300 games at 25 data points per second. We split the data into more than 113,000 possessions, which equals approximately 305 hours of gameplay. We look at the problem of predicting an individual offensive player's trajectory. We take as input the recent trajectories of all players on the court, as well as the ball and the shot clock. We predict multiple possible trajectories and associate a probability with each of them. Note that in the paper, we show that predicting velocities results in better paths than predicting waypoints of the trajectories. You can find more detailed results in the paper. The key to successfully train the network is our proposed loss function. We adapt multimodal loss, which consists of the mean squared error of the trajectories, which is added to the log likelihood of the best predicted trajectory. M star stands for the predicted trajectory that is closest to the ground truth. Previous versions of this loss function followed a similar procedure, but where epsilon is equal to 0. This means that only the best trajectory gets updated. We found that this leads to mode collapse, where poorly initialized paths never get trained. To fix this, we set epsilon to 0.25 and linearly anneal it to 0 over multiple training epochs. In this figure, we visualize the predicted trajectories of one offensive player. The three pictures show the same game situation, where offensive players are shown as red dots, defensive players as blue dots, and the ground truth trajectory is shown in green. On the left side, we see a single predicted trajectory of the baseline macro VRNN, which is a variational autoencoder that is specifically designed to generate basketball players' trajectories. The trajectory shows some unrealistic behavior, and the predicted path goes out of bounds. The middle image shows 4 paths predicted by SocialGAN, which is a state-of-the-art pedestrian trajectory prediction approach, specifically for crowded environments with a lot of human interactions. The paths are plausible, but show little diversity. The right side shows our approach, together with a relative likelihood for each of the paths. Our generated trajectories are smooth, plausible, physically achievable, and show good diversity. A detailed results table with quantitative results can be found in the paper. We note that we evaluated on 3 different measures: average displacement error of waypoints, final displacement error of final trajectory location, and mean squared error of velocities. The baseline macro VRNN shows some physically unachievable paths with accelerations up to 54.9 meters per square second. The ground truth contains maximum accelerations of 14.5 meters per square second after removing noisy outliers. In comparison, the paths generated from our approach are physically achievable for the players, with a maximum acceleration of 12.2 meters per square second. We thank you for your attention.